Today we're learning about allylic and benzylic reactions.
Today we're going to be going over allylic and benzylic reactivity. And so I want to first go over some nomenclature for this. For allylic systems, we have this double bond, and it's this position that's right next door to this double bond that we call allylic. This often gets confused sometimes when we look at the position that's right on the double bond. This carbon here, we would describe this position as a vinyl position. So you are going to hear me refer to the position that's right next to that double bond as allylic. And then if we look at a benzylic position, it's very similar. Here we've got benzene. It is the position that's not on the benzene ring, but it is the position right beside it here. Now, many times I see people get confused with a benzylic position versus an aromatic position here. And so I just want to highlight something that if we have this group, I know this is going to look confusing, but if we have this group attached to something, we would call this, which is kind of weird, we would call this a phenyl ring. If we're talking about the chemistry that's on the carbon right beside the benzene ring, that is benzylic. And what we're going to do is we're going to look at the difference in reactivity and why these positions are so special. This is a review from some of your material from Chem 343. Here I've got carbocation formation and what we know as SN1 reactions. And we know from our studies that SN1 reactions first start with the formation of a carbocation. Here I've got this chloride on a tertiary position. There are 3 carbon groups attached to this carbon that has the chloride, our leaving group. Our first step of the reaction is going to be loss of this chlorine. This is going to form our tertiary carbocation. One other thing we've learned about SN1 reactions is it's also called SN1 because this is unimolecular. The rate of the reaction is determined by the formation of the carbocation. It is determined by just the chemistry done on our carbon with a leaving group. If we then add our water, I'm going to have an oxygen with 2 hydrogens still attached. The oxygen now has a positive charge. You could also imagine the water removing this proton. We're going to use the chlorine here in this example. We're going to remove that proton, and now we have our desired SN1 product, this tertiary alcohol. What I want to do now is look at what we would call an allylic chloride. So here we know that this position is our allylic position, right? That's what we just talked about. Now let's look at what happens when we do an SN1 reaction with this type of system. Again, our first step here is loss of our leaving group. We're going to form an allylic carbocation here. Here we have a carbocation on a tertiary position, very similar to the reaction I showed before. The cool thing about this one is we have this double bond that can show another resonance structure, showing this carbocation is even more stabilized. In this case, our double bond can move over, and we have 2 resonance structures that describe this carbocation. Another way we like to look at allylic systems when we have this carbocation is to describe our resonance structure highlighting this positive charge going between these carbon atoms, you'll see that this side is partially positive and the side over here is partially positive. This is another way to think about this. Both of these carbons are partially positive. If we react this with water, there are two positions we could essentially add water to. And this is in fact what we do. Here, if I have water attack our carbocation here on the end, followed by deprotonation, I form this alcohol here. Another way we can react water is with our other resonance structure here. You can imagine now we could also have the water attack at this position. Again, our oxygen has a positive charge, and now we will deprotonate. In this case, you would get a mixture of products for these two. What I want us to notice is that when we have an allylic system, this carbocation is resonance stabilized, as you can see here. This resonance stabilization is depicted here. And what you'll see is that there are two positions that can be attacked. We have two positions here that are partially positive on our allylic system. This makes these very unique. We will discuss the rates of these reactions in just a little bit. Before we do that, I want to go over a benzylic system so we can also get an idea about what these systems like to do. Here we have, again, we have a chlorine leaving group. We're going to do an SN1 type reaction. The first step of an SN1 reaction is loss of our leaving group. We have our tertiary carbocation, which we know to be very stable. Now we're going to have water attack our carbocation here. Again, we have an oxygen with a positive charge, and then we need to remove our very acidic proton there, and here we have our desired alcohol. Let's look at the next reaction. And in this case, again, we have a special position here. We have our benzylic position. We have this benzylic chloride. And so here we're going to have the chlorine leave, and we're going to make this benzylic carbocation. Now, one thing you'll notice about this carbocation, we're going to use some of what we had practiced in our last unit with electrophilic aromatic substitution reactions. You'll notice that we have a positive charge here, and it's directly attached to a benzene ring. We can utilize a lot of the same resonance structures that we drew in our last unit. I'm going to use a blue as a different color here as we look at the resonance structures. You can imagine that this aromatic ring could push electrons out, forming this resonance structure here. We can push another double bond over to form this resonance structure. And then we can form one more here. What you'll see is that carbocation is stabilized over 4 different structures, as I've shown, but 4 different resonance structures. Now you might ask yourself, well, in the allylic example, we saw water add to either one of them. Now, this isn't quite the case for the benzylic example, and this is because of what we learned about with aromaticity and its special stabilizing character. So in this case, if we were to add water on one of the blue resonance structures that I have shown, you would lose the aromaticity in your compound. This is not thermodynamically favored, so that would be one reason why that you would not have water attacking one of the blue resonance structures I have shown. Our product would not have that extra stabilization from the aromaticity. And this is indeed what happens. We do not see water attacking our blue resonance structures. We see water attacking at the benzylic position. So here we're going to have water attack our benzylic position. We have an oxygen still with the two hydrogens here, positively charged. And then we're going to take our chlorine and deprotonate. Again, you could use water as well to deprotonate. There's usually excess of our nucleophile here. And here we have our desired alcohol on our benzylic position. Now, one thing I want to do is I want to look at the energy diagram for this. We talked some about how we're first going to be forming our carbocation. So let's look. In our reaction diagram, again, we have our energy. This is the progress of the reaction. We start here with some kind of an R with a leaving group. So here we'll just look at our chlorides as our leaving group. We know that first we will go through a transition state, make our carbocation, and then here we're going to go to our products. So this position here is the structure of our carbocation. We know that this reaction is energetically uphill. So again, we've got RCl. We're going to turn it into our cation, and then we're going to react it with some nucleophile. In this case, we're using water. And so when we look at this, we can still apply our Hammond's postulate because we have a very uphill first reaction. And if this is the case, then the transition state, which is here, will be energetically and structurally similar to our carbocation that we're forming. This also means that if we can stabilize that carbocation, we can essentially make the reaction go faster. We will have a faster reaction rate. And in this case, this mimics a lot of what we learned with the rhenium cation chemistry with electrophilic aromatic substitution. The same kind of thought process applies. If we stabilize our carbocation, the reaction will go faster. Take, for example, what if we do stabilize our carbocation? What we will see is that the reaction indeed will go faster. And so again here, this is our delta G double dagger. And you'll notice that this energy is here for a more stabilized carbocation is lower in energy. What we can do now is compare the different reactions we've just gone over. Let's go back to our allylic system. In this case, the reaction rate here is described by, again, like we talked about, the formation of our carbocation. So essentially, a more stable carbocation would lead to a faster reaction. And in this case, if I compare a relative rate, so here I'm going to write in blue, my relative rate, if I were to say that this rate were 1, the SN1 reaction within this allylic system is 160 times faster. And this is because of the stabilization of that carbocation. Let's look at our example here. We've got our benzylic system. And they're both these tertiary carbocations, but the benzylic system, like we saw in our blue resonance structures, is significantly showing more stabilization. That carbocation is now lower in energy and the reaction rate is indeed faster. In this case, our relative rate is about 1 to about 620. Again, these benzylic and allylic systems show increased reactivity at those positions. This is a lot of the chemistry we're going to talk about. Let's take, for example, what happens if we were to compare these three reactions. Again, we've compared this one. Again, relative rate. This one's 1, 620. What happens if we add a methoxy group to our benzene ring? Again, you'll notice we've got these tertiary positions, but this one is benzylic. Let's go through this reaction with this methoxy substituted benzene ring. Again, our first step here is going to be loss of our leaving group here. We are going to be using some of the concepts that we learned in our electrophilic aromatic substitution work. So here we've got a benzylic carbocation. Let's dive in and look at our resonance structures for this. We're going to use a lot of the same things that we've learned before. In this case, we have this positive charge on our benzylic position. That means that we can push the electrons outside of the ring. Again, we can push this over here. We can also now use our oxygen from the methoxy group and we can form this resonance structure here. And there's one more resonance structure that we can draw. Again, in this case, we have additional resonance from our benzene ring. This benzylic position is more stabilized. The loss of that chloride is going to happen faster, and we'll talk about the rate. One thing you'll notice with this substituent here is that we're able to stabilize this even further. And we've talked about this before. This methoxy group here in this resonance structure, every atom in the resonance structure has a full octet. And so this resonance structure has a major contribution to the stability of this carbocation. And so in this case, we can still look at this and wonder, well, where is water going to attack, right? Again, we talked about how if we attack on any of the positions where we do not have aromaticity, where we lose aromaticity in the product, that would be thermodynamically disfavored. And so in this case, again, we would have water attack our benzylic position. We still have an oxygen now with 2 hydrogens on it. Again, it's positively charged. We can now remove one of those protons so we get our neutral species and our desired alcohol. Now, one question you might have is, well, what about this reaction compared to the one listed right above, this unsubstituted benzene ring? Let me draw in here again. Let's practice again our carbocations here. Here we've got a tertiary. Here we've got our benzylic. And down here with our 4 blue resonance structures also showing the methoxy donating into the ring. Again, we should look real quickly at how we can also describe this like we did our allylic system. In our resonance structures, we have these partial positive charges on the 3 positions on our benzene ring as well as our benzylic position. And the same occurs here in this methoxy substituted one. What's really cool about this one, this relative reaction rate, the stabilization of that carbocation increases the rate tremendously. Our relative rate, I can't even write it on the side here. It has a relative rate of 2 million compared to our tertiary carbocation that was forming. And so as you can see, benzylic and allylic positions are very special and they have enhanced reactivity. We're going to look more into this and see what other type of chemistry that we have learned before, and we're going to apply it to our new concept of allylic and benzylic positions.